Hi, class. Welcome to the next section, chapter 10.6. Today we're going to talk about biology applications. So the first thing we're going to talk about is blood flow. So a laminar flow is flow with no turbulence. Velocity of a liquid through a tube that has a length of L and a radius of R can be modeled with the equation velocity depending on the radius that we're at within inside of the tube, is P over 4 eta over times L times radius squared minus R squared. So little r here is our variable. Everything else is a constant. Okay. P is the pressure difference between the ends of the tube. Eta is the viscosity of the liquid within inside the tube that's flowing. Little r is our variable. It represents the radius length from the exact center of the tube to the end. So if we're looking at how blood is flowing, or any flow, we're going to be talking about blood, but any liquid is flowing at the center, we would call r equals 0, right? If we're a little bit in between, if, let's say halfway between the end radius and the center, it would be half of big R, right? Would be the radius. So our variable takes on values between 0, dead center, and large R, which is the outer radius of our tube, okay, or the distance from the center to the edge, the inner edge. So the flow in the center of the tube is always faster than the flow at the inner edges of the tube due to friction. And so laminar flow is that effect that you get when you have water running through a hose or oil that's leaking out, where you can't tell that water is actually flowing and everything looks like a standstill. So basically what's happening is every atom is basically following exactly the molecule of water behind it, right? So every molecule of water or whatever liquid is following exactly the molecule of the liquid in front of you. So it could be an atom or it could be a molecule depending on what the liquid is, right? So the flow in the center is always faster because what's happening is everything is following right behind um, the molecule or atom that's in front of it. So the flow in the center is going to be the fastest because there's the least amount of friction, right? At the edge of the tube, you're going to get friction, right, on the inner edges. So when we're looking at an integral, we're looking at the slice of the pipe and we're integrating across that face of the pipe. Okay, so our slices are going to be rings from the interior of the tube towards the outside, and we'll look at the velocity inside of each slice, right? So here is our tube. This is one end, this is the other end. Okay, it has the length of L, or at least this section that we're looking at has the length of L. Here, when we look at a slice, it'll have a thickness of delta little r, right? So a slice of a ring. Um, the distance from exact center to the inner edge of the tube is large R. Okay. And so then when we take our little slices, um, the width of this ring is the width of this ring, right? So this is us just taking the slice here and kind of like translating it so we're looking at it face on. And so the width here is delta R. Okay. Here, this inner radius is going to be R, I minus 1. And the outer edge is Ri because again, this is just a slice. Our slice could have been at any diameter along this height. And so the difference for delta R is Ri sub 1. It's the difference between R sub I and Ri sub 1. Okay. So again, the change in R is R sub I minus Ri sub 1. So that's how we're taking our slices. And then the easiest thing to do here is to use the cylindrical shells method. Okay, so we can find the volume that passes through L in a unit of time. Flow is also known as flux, okay, or discharge, which we label as capital F. You'll note the difference between flow and force by context, although flux could be a force. So this is the rate of flow. Okay, flux is the rate of flow. So capital F here is 0 to r, 2 pi times the radius times the velocity through whatever slice of a radius that we're looking at, right? So this is through the cylindrical shells method, okay? So I'm going to integrate with respect to little r, okay? So our v of r, velocity at whatever distance away from the center, has the formula, which we just went over, right? Right here. And so that is where the substitution comes in. So 2 pi r, and then our equation for flow, right? Um, Laminar flow. And so here we can pull out all the constants. The 2 over 4 gives us a 2 in the denominator. There's a pi in the numerator, right? There's this capital P for the pressure difference in the numerator, and eta and L, the length of the tube, are on the bottom. All of the R's are on the inside. This big R we cannot separate away from the equation, so it is inside our equation. We pulled out that constant term. Here, the next thing I want to do is I want to multiply this R through. It'd be a lot easier to integrate once I do that. And again, remember R squared, large R squared is a constant. Okay, so this R goes to a square. We have the 1/2. This goes up to the 4th power, and we multiply by 1/4. So if we evaluate at 0, this R and this R make everything 0. So we really only have to plug in a large R for everything. So when I plug in, so let's see what's going to happen here. When I plug in large R, I'm going to have R to the 4th. When I plug in large R for little r, I'm also going to have another R to the 4th. So I can do some simplifications on the inside of this parentheses of this bracket. And so 1/2 minus 1/4. So 1/4 is half of a half, right? So this turns into just a positive 1/4. Okay. And now we can start to, well, the only thing we can really do is combine this 2 and this 4. So this turns into an 8 in the denominator. And that is our formula for flux or discharge or rate of flow of a liquid through a tube of length L. Okay. This is known as Poiseuille's law. Poiseuille's, I'm probably saying this really, really wrong. Poiseuille's law. Anyways, cardiac output is related to this. So for cardiac output is the volume of blood that's being pumped by the heart per unit of time. So per second, per minute, whatever you want to use. Typically, we go how many beats per minute. So it's the rate of flow into the aorta. So cardiac output is measured by inserting dye into the heart and measuring how much dye then leaves the heart through the aorta. So here, A is amount of uh, dye that's going to leave the house or leave the heart. I'm sorry. Here, F, this is that flux. This is the flow through the heart, right? From 0 to T. So through some moment of time. C of T, which is, I don't remember at this moment. So A is the amount of dye. C of T is the concentration of the dye at time T in the heart. And we can manipulate this equation and solve for F so that we have a formula for flow through the aorta. Right? So that's what we shouldn't know. And so we divide both sides by this integral amount, and that's my formula, right? So the amount of dye that I use divided by the sum of the amount of dye, the concentration of dye left over from 0 to T. Okay, so up to whatever moment, what was the amount of time, what was the amount of dye that passed through the heart? Example, so high blood pressure happens when the arteries constrict. Okay, in order to keep the flow rate regular, the heart pumps harder. Okay, so what's happening is for high blood pressure, you might have clogged arteries or whatever the case is, but the arteries are constricted. So either they are constricting themselves or they are blocked, so then blood flow is restricted, right? In order to maintain the amount of blood flow that is happening, that needs to happen, the heart has to pump harder in order to maintain that ideal level of flow, right? So to keep the flow rate regular, I have to pump harder because there is an obstruction or there's a constriction. The tube that I'm going through is smaller, right? So this is going to increase the pressure. If I have to pump harder, there's more pressure that is going through the arteries, the pipe, what have you. Okay. So using the previous law, Poiseuille's law, to show that um, it's the initial radius, right, outer radius, and the initial uh, pressure are normal values of the radius and pressure in an artery, and the constricted values are R and P, right? So if I start with R naught and P naught, um, where this is how wide um, the tube is, right? The artery is initially, and this is the initial pressure. And then this is the constricted values where R is now smaller than R naught, right? I have a constricted value, and then my pressure then is higher than P naught, right? Then for the flux to remain constant, right, the flow has to remain constant. P and R are related by the following equation. So the ratio of the ending pressure that's higher over the initial pressure is equal to the initial radius over the new smaller constricted radius to the fourth power. Okay. We want to deduce that if the radius of an artery is constricted to 3/4 of its normal value, then the pressure is tripled, right? So we're going to say, so if the radius is constricted to 3/4, so that means that this ending R value, the ending radius, is 3/4 of the size of the initial radius, right? So it's 3/4 the amount of what it was before. So it's shrank by 75%, or to 75%, I should say. Okay. So my initial flow has to equal my new flow, right? Because the constriction changes and the pressure changes in order to keep the flow rate the same. So my initial flow and my ending flow rate are equal in value. So if I just substitute in those values, right, we have this formula for F that we derived, okay, through a tube, radius of inner radius R, length L, and so we're just going to substitute that. Okay, where are we? Sorry, oops. Here we go. So it's pi p r to the fourth over 8 eta and the length. And so my initial flow rate has P naught and R naught in it. My ending flow rate has my ending P pressure and my ending inner radius of the artery. So cancel out all the stuff that's the same, right? This pi over 8, this I have pi on both sides, so I can divide both sides by pi. I have 8 on both sides, so if I multiply everything by 8, that goes away. The eta and the L, right? So the only thing that really remains is P naught and P, R naught to the fourth, and R to the fourth, because these values are different. These are initial values. These are my terminal values. Okay, everything else is the same, so I can cancel them out. If I divide, it doesn't matter which one I divide. Let's say divide by R naught on both sides and then large P on both sides. I get a ratio that's the same thing as this, right? I can change the order if I need to in order for it to match the equation, right? So we showed that flow rate has to remain the same, okay? And it's related by this equation, right? The pressure ratios and the inner radius ratios are have this relationship. So if I'm saying that big R, right, my ending ratio is 3/4 of the size of the initial uh, radius, I just make that substitution, right? So where I used to see R, I replace it with 3/4 R, and I just do my deal. So obviously here the R naughts will cancel, and this 4/3 is not, or 3/4 is in the denominator, so it gets to reciprocate and get multiplied to the fourth power. So this turns into 4 over 3 to the fourth power is equal to P over P naught. Okay. So from here, I can multiply this out, right? 4 times 4 is 16. So this is 16 times 16, which is 225, I believe. And this is 3 times 3 and 3 times 3. So 9 times 9 is 81. Okay. Oh, sorry, 256. So 256 over 81 P naught, which is just about, if I were to plug this in a calculator, around 3.16, which is larger than 3. And remember what my question was um, deduce that if the radius of an artery is constricted to three quarters of its normal value, meaning if the ending amount of the inner radius is three-quarters the amount of what I started with, then my pressure is tripled, right? And so what do we get here? I got that this value, right? My end pressure is this amount times the initial pressure, which is around 3.16, which is more than 3. So my terminal pressure is more than 3 times my initial pressure. So it more than triples the initial pressure. Okay. Hope this makes sense to you. I will see you guys on the next section, which is the last section for chapter 10.